Yeah, thanks, and thanks for this opportunity to try and give you a very brief overview of the different kind of photonic systems, like a taste of the photonic systems that we use and rely on at Swissfel, which is part of the Scherrer Institut. So, just an outline. So my role at the institution and my background is I'm responsible for what we call the X-ray photon diagnostics. So all the different schemes and methods we have for measuring and understanding the X-ray pulse that our machines are producing. As I say, I'm going to give you a highlight of 3 of the photonic systems that we use. But first of all, we've heard about already different types of accelerators to produce X-rays and photons of different energies. And if we want to take out a simple message of what makes FELs different from other types of accelerators, and especially compared to synchrotron accelerators, is that a free electron laser produces pulses with sort of an unprecedented peak brilliance in the X-ray domain. In this case, FELs can go from the infrared to the very hard X-ray regime, but in this case we're talking about soft and hard X-rays. But the point is that we have very short pulses with very high peak brilliance in ultra short pulses, and importantly with a full transverse coherence. And the key aspect for a FEL to produce these pulses is kind of an ordering process you could I think of called SAZE, where by the spontaneous emission of a high energy and accelerated electron that is going through a oscillating magnetic field, the spontaneous light that's produced kind of amplifies itself in a similar way to a laser cavity. Not strictly the case, so but that's where the laser name comes from, so that we have a clear amplification of the X-rays through what we call these undulators. And then with these high peak brilliance pulses, we use them for a range of applications to study biological, physical, and chemical systems, where with a high peak brilliance, we can develop new spectroscopic methods where we can take key advantage of the site specificity that we have with X-ray photons. So just a couple of examples here are developing new spectroscopic methods to take advantage of the short pulse of our X-rays, and also to another application is measurement of structural and functional dynamics in biological systems, where you're actually relying on the high peak brilliance to use your X-rays to image of the biological system. But most importantly is that all the photons that go through that system travel through in a short period of time before the system that you're trying to study starts to break up. So this idea of diffract before destroy. So a machine like Swissfel is a 700-meter long machine, so it's kind of in the let's say the medium range of sizes. So a lot shorter than places like European Excel and of course CERN, but then kind of a medium-sized facility where there are different distinct parts, where the electrons, which are accelerated in our case up to about 5 GeV, go through a series of accelerators after the initial injector, and then the electrons afterwards are then also go through a series of undulators, where this oscillation process produces the X-rays, and afterwards then the X-rays can be distributed to a series of user end stations, where the key difference with a synchrotron and the FEL, as well as a synchrotron, can have multiple users using the electron beam at one time. Here you have one electron beam and one user. So the cost per experiment is significantly higher. So at Swissval, then there are two operational machines where we have two electron bunches that go down the accelerator at 100 hertz with a slight delay between them. So we have two parallel operations, one in a soft X-ray called Athos, and one in the hard X-ray called Aramis. Now, if we think the so as I said, we're cited at the Paul Scherrer Institute in the forest. So it's sort of semi under the ground in the Verlinger Wood, which is and nicely kept open to the public, so you can walk right over the building, which is fine. But then it gives us some limitations in what we can do with the electron beam inside the building, where we have the two parallel accelerator lines, we see in the top side. So we use a copper linac for the acceleration, and then these series of undulators down in the blue we see here, where the photons are created. Now, the key purpose really of a short pulse experiment, and maybe which is different when we think about synchrotron type measurements, is often why we care about short pulses, is to follow dynamics. So imagine we have some system where we know we have some molecular system where we have some electron density in state A, and we know it goes into state B. But the question we really need to know is how does that transition take place? So we can do that with a method called pump probe, where we use two pulses, where one of those pulses can be an X-ray pulse. Two of those pulses could be X-ray pulses, but what is more commonly used is one is an X-ray pulse and one is a visible or terahertz or mid-infrared laser pulse. And by initiating some state change from state A with what we call the pump pulse, so that could be, say, a UV photon from a synchronized laser system synchronized to the X-ray system, we can vary the delay between the pump and what we call the probe, which is the red pulse here, which could be the X-ray pulse, where we see some diffraction from the electron state. And by delaying the time between these two pulses and then collecting some variable, what we see is we can delay those, and whilst we will measure a system, we'll measure a blue curve like this that gives us an estimation of how this system changes. So that's the kind of fundamental measurements that we do with the time resolved FEL. So just a quick overlook of the main photonic systems. The most important, the start of the whole system is that we have a cathode that produces X-rays, and this is done by photo emission of a copper cathode from what we call the gun laser system, where this has to be an extremely reliable system that can run in an environment with which is it's not accessible to the engineers as it's running, and we require an extremely stable pulse energy stability, where on the intensity, the shot-to-shot intensity difference is so 0.005 or less RMS. And the system here is a ytterbium based system of 450 femtoseconds, but only running at 100 hertz, which is the repetition rate of the system. So this is then doubled and tripled to produce a pulse, which is then impinges on the copper cathode and produces the initial bunch of electrons, which are then accelerated down the amplifier. The second new application of lasers and photonic systems on the electron bunch is we can actually use an external laser field to modulate the electron bunch itself to make the FEL more laser-like itself. So this requires a large laser system halfway along the tunnel, which is then coupled into the electron accelerator, and the co-propagating intense laser pulses and electron bunches causes a modulation, which is then used to produce very stable and very short X-ray pulse trains. And the laser system that's used there is a 15 millijoule TISAF system, where we require the high pulse energy, but then, to be honest, the shot-to-shot stability and pointing jitter causes more of an issue. And for a system like this as a facility, then the actual running costs of the large pump laser systems that are required is also a significant cost that has to be calculated when these are used for certain experiments. Another main application of photonic systems, as we heard a bit before, is the timing and synchronization system, which is all laser-based with a whole multitude of systems coming from a 10 megahertz reference signal, where all of the timing diagnostics, the external laser systems that are used in the pump probe measurements, the timing and the we have a unique system for tagging every pulse that we produce with a unique pulse ID, relies on this optical system, which is then distributed over the 700 meters of the facility. And the timing and synchronization is one of the key systems that ultimately gives us the time resolution of our system, of our experiments. We then use similar, different kind of photonic-based systems or optical systems for the diagnostics of the X-rays, where we use a lot of imaging and spectrometer systems to measure the shot-to-shot, so 100 Hertz pulse properties from the X-rays with a high fidelity. And another sort of jumping around now, but another important system is what I told you about is the timing jitter. Whilst even with the world's best or maybe world's good timing and synchronization systems, you can't remove the fundamental jitters that exist when you want to use, if you're producing attosecond pulses with your X-rays and want to use an externally locked laser system as a pump probe in that, then you really need to have a single shot ability to measure the timing difference between your laser pulse and your X-ray pulse. One method that we use for doing that is we probe the refractive index-based change on a semiconductor, which is actually pumped by the X-ray pulse. And by coming in with a chirped white light pulse, we can see where we see a change in the reflectivity of this material, where maybe this video will play. And as we actually delay the arrival time between the X-ray pulse that perturbs this system and this chirped white light pulse, for example, here between 500 and 600 nanometers, we can measure a small change in reflectivity, and by fitting this edge, we can tag the relative arrival time between these laser pulses down to a femtosecond or a few femtoseconds in our time resolution. So I think just looking for the future, we have at the moment two beamlines running Aramis and Athos, and in the coming within the next decade, we hope to have built a third arm called Porthos, where it expand from 6 end stations to 9 end stations. So yeah, that's what I wanted to briefly share with you today.